Good day. Welcome to Machine Elements. Acceleration Analysis, topic number 6. At the end of this lesson, you should be able to describe the method of finding acceleration using velocity and acceleration polygon. Determine acceleration of a point in a linkage using semi-graphical approach. So why is it necessary to analyze the acceleration of the various points or components of a machine? So with the advent of high-speed machines, the accelerations of the moving parts are becoming more important. The inertia forces produced by the accelerations of the links in a machine may be of a high magnitude, and in some cases, at a certain position, may be higher than the forces produced by the working medium. The obtaining of the acceleration of points in the links of a machine is prerequisite to the making of an inertia force analysis of the machine. In this topic, the acceleration in machine members will be discussed. The method developed to be similar to the relative velocity method treated in the previous topic. It is now called the relative acceleration method. So if you look back, there are two components of your velocity. And velocities can change in magnitude, direction sense, and even both magnitude and direction sense. A particle whose velocity changes both in magnitude and direction at any instant has the following components. The first component is the centripetal or radial or normal component. So this component is referring to the rate of change of the velocity in the direction sense. This component is perpendicular to the velocity of a particle at a given instant. The second component is the tangential component. This one is referring to the change of velocity in terms of magnitude. And this one is parallel to the velocity of the particle at a given instant. So we are going to analyze these two components in order for us to arrive at the acceleration of the particular point. Acceleration, on the other hand, is the rate of change of velocity with respect to time. So if you can recall, if the velocity is constant, or if the velocity does not change, then our acceleration will be equal to 0. And if the velocity changes with time, then the rate of change of that velocity is referred to as acceleration. Just like velocity, acceleration is a vector quantity, and just like velocity can also be linear or angular. Linear acceleration is denoted by the symbol big letter A for this subject is equals to the rate of change of the velocity over the rate of change of time. While angular acceleration is the rate of change of your angular velocity with respect to time. So we use the symbol alpha for angular acceleration. Acceleration has also two components. So we have the radial or normal acceleration. So this acceleration is given by the equation the omega squared, or the angular velocity squared of that component, multiplied by the radius or the radius of curvature of the point from the center of rotation. As you can see here, that is AB. Since we know that our angular acceleration is equals to velocity over the radius, then we can transform our equation of radial or normal acceleration to the velocity of the point, the linear velocity squared divided by the radius. Here in our diagram, the radial or normal acceleration is along your radius, and at the same time it is towards the point of rotation. So here our point of rotation is A, so the center of rotation of point B. So our normal acceleration is moving towards that center of rotation. So that is our radial or normal acceleration. The other one, we have tangential acceleration. From the term tangent, so this one is perpendicular to our normal acceleration. And this is given by our angular acceleration or alpha times the length AB. So as you can see here in our diagram, our tangential acceleration is normal to our normal acceleration. It is perpendicular also to our link or to our link that is rotating. So you can also see here if our acceleration, angular acceleration and angular velocity are of the same sense, then this point is accelerating. If acceleration is of the opposite side or opposite rotation as our angular acceleration, then this point is decelerating. I hope that basic concept or component of acceleration is clear to you. So again, our normal or radial acceleration is moving towards the center, while our tangential acceleration is perpendicular to the rotating link. So let us analyze acceleration in terms of linkage. So how do we find the acceleration for points in a link? Say for example, you have this link. Here. So first step in constructing your acceleration diagram is that from the given link length EB and angular velocity, so you solve for the velocity of a particular link, which was also discussed in topic number 5. Secondly, solve for the radial and tangential acceleration by using the equations that we have in the previous line. So that is given here. So take note that for us to have radial and tangential acceleration, the length AB must be given. The angular or linear velocity must also be given. And the radial or angular acceleration must be given as well. So our acceleration can be resolved into two components, radial and tangential. So from any point Q, draw the vector length which corresponds to our radial acceleration parallel to the link EB to represent the radial component of the acceleration. Here you have this our vector length by substituting the given values to this formula, then we can get the radial component of the acceleration. So to draw that, you designate a point Q anywhere on the paper. Draw the vector length which represents our radial component. The radial component must be parallel to the link EB because as stated a while ago, it should be towards the center, and it is parallel to the link AB. So this is our link AB. So our radial component must be parallel to this particular link. So you draw that from point Q, representing the acceleration scale of your radial component of the acceleration. So as we have this one, as you can see, they are parallel. So that is parallel to our link AB. The next step is to draw from the terminal of the radial component of the acceleration, draw the vector length which corresponds to the tangential acceleration. It should be perpendicular to the link EB or to our radial component. So as you can see here, it should be perpendicular to AB. And it should be drawn at the terminal of the radial component. The terminal of the radial component of the acceleration. So it's like using head to tail method. So radial, and then we have tangential. And then finally, draw a line from Q to the terminal of the tangential component of the acceleration. As you can see here, so using head to tail, we just connect from the point of origination or the pole or Q, the head of the tangential component of the acceleration. Thus, we are able to find the absolute. So this is the absolute acceleration of the link EB. As you can also see here, our radial and absolute components of acceleration, they originate from the pole, while the tangential component originates from the head of the other vector. So let us analyze this further. So let us take note in this analysis that the angular acceleration denoted by the symbol alpha can be of different direction. With respect to the angular velocity. So it could either be angular acceleration is counterclockwise and then angular velocity is clockwise. So it means that our object is decelerating if they are at the opposite direction. If they are the same, then it must be accelerating. The second point is, this is what I'm trying to say, that if our angular velocity is counterclockwise, and if our angular acceleration is clockwise, this means that the link is turning counterclockwise but is decelerating. So the link is moving in the direction of the angular velocity, but this is decelerating. And the direction of the tangential acceleration, this denoted by alpha subscript T, is always the same as with the angular acceleration alpha. So the direction of the tangential acceleration is always the same direction as the angular acceleration. Say for example, you have angular acceleration that is clockwise, then the tangential acceleration will also be of the same sense as the angular acceleration. So it will not abide the direction of the angular velocity, but it will abide the direction of the angular acceleration. So we will demonstrate this later on for you to be able to understand these three concepts. So now we have the equations for total acceleration. So from the diagram that we draw a while ago, we can infer that the absolute acceleration, our absolute angular acceleration, is just the vector sum of the radial component and the tangential component. As you can also see here, we have the radial component and then the tangential component. So our absolute acceleration is just the vector sum of those two components. And the angle theta, which is the resultant acceleration vector direction with respect to the link AB, is expressed by the equation, this equation. This one here is your the direction of our absolute acceleration with respect to the link AB. So let us also take note that the absolute linear acceleration of one point on a floating link is equal to the vector sum of the absolute linear acceleration of a second point on the link, the normal acceleration of the first point relative to the second point, and the tangential acceleration of the first point relative to the second point. So what I am trying to say here is that usually we're only given with one point with known velocities and acceleration. And then we are required to find the acceleration and velocities of the other points, just like what we did in topic number 5. So for you to be able to get the acceleration of the other points, you may use this concept that the absolute linear acceleration of the other point on a floating link is just equal to the vector sum of these quantities, like absolute linear acceleration of the second point and the normal acceleration of the first point relative to the second point, and the tangential acceleration of the first point relative to the second point. This is denoted by the equation. So we have, if we are looking for example, the absolute acceleration of point B, then for you to be able to get the acceleration of point B, it is just the sum of these vector components. We have the normal component of absolute acceleration of A, as well as the tangential component of A, plus the normal component of the absolute acceleration of B relative to A, and then the tangential component of the acceleration of B relative to A. So in this way, we can still solve for the absolute velocity, angular acceleration or acceleration of the other point. If, for example, you have here 2 points A and B, then the velocity of A is known, as well as the direction of A is known. So you have to recall how to draw again the velocities, velocity polygon using relative velocity method as discussed in topic number 5 for you to be able to master this topic. On the other hand, the direction of the absolute acceleration of A is also known as seen in the diagram. So you have here point A, of which the absolute velocity and then the absolute acceleration with magnitude and direction is known. And then we have a point B connected to point A. So they are on the same link. So point A and point B are on the same link. It's just that only the direction of the velocity of B as well as the direction of its acceleration is known. So M and N here represents the direction of our B. So our N represents its velocity, while M represents its acceleration. So we are looking for the absolute velocity of and the absolute acceleration of point B. So using the concept that we learned, so we have unknown, we are looking for the absolute linear acceleration of B as well as the absolute angular acceleration of the link AB. So we are looking for the angular acceleration of link AB and then the absolute linear acceleration of B. So from our formula, we can determine the absolute linear acceleration of b by using this equation. So we just have to find the components of the linear acceleration of point A, as well as the relative acceleration of B with respect to A. If we are going to decompose this equation, since we know that acceleration of A is just equals to the sum of these two components. The normal and the tangential component is just equal to the absolute linear acceleration of E. And then we also know from the previous equation that we can resolve this, the normal component of the relative velocity of B with respect to A, in terms of the velocity of B with respect to A, and then the length of the link AB. That's why we have this one here. And then the tangential component as the product of the unknown angular acceleration of this link AB and the length of AB. As you can see here, we have two unknowns. So we do not know the value of this one, and we do not know the value as well of this one. As well, they are actually part of the unknowns. So we will solve for these values for us to be able to solve this particular case. Now, the first step in analyzing using relative acceleration method, if you can still recall, we have relative velocity analysis method. It's almost the same method. We need to draw the velocity as well as the acceleration diagram, and then use that diagram to find the length as well as direction sense of the velocities and accelerations of the various points. Using this method, we can also solve for the velocity as well as angular acceleration of floating links. So what you're going to do is to designate a point Q and then draw the velocity polygon. So we know the velocity of A, so that's why we just have to connect it on the same direction sense and magnitude as the given from the pole Q. And then since we know the direction of the velocity of B, that is n, so the velocity of B is unknown. So remember that we are still solving for the velocity polygon, just like what we did in topic number 5. So the direction of B is known, that is n, that's why we connect another arbitrary line Q from Q, which is the same direction sense as n. It does not have to be of the same length as this, but it just have to be of the same direction sense. From the previous topic, we learned that we can get the absolute velocity of B if we are going to connect A to, if we're going to draw a line that is perpendicular to AB from the head of A, right? So we draw a line from the head of A that is perpendicular to AB. Because we learned from the previous topic that our velocity polygon is, the lines in the velocity polygon is perpendicular to the lines in the actual mechanism. So as you can see here, they are perpendicular. So this from the head of A. In this way, we were able to obtain the velocity of B, that is QB. So this now represents our velocity polygon. So this is the first step in drawing the relative acceleration polygon using the relative acceleration method. The next step is now to compute the value of the normal component of the relative acceleration of B with respect to A. So this means relative acceleration of B with respect to A normal. So we already have the formula for that, and that is equals to this one. So the velocity of B with respect to A squared divided by AB. This is also the reason why we have to draw the velocity polygon, because we need to find the length of A to B, because our A to B represents this velocity of B with respect to A. You just have to measure this and then plug in the value so that you can get the relative velocity, the relative acceleration of B with respect to A normal. Now we have this one, so we just have to solve for the tangential component. For the tangential component, we will draw the acceleration polygon. So again, designate a pole Q anywhere on your paper. So we have here point Q. And then just draw the absolute acceleration of A, the same direction, sense, and magnitude as the actual acceleration. Yan, as you can see. So this is now the acceleration polygon. So we learned that the normal component of the acceleration, so the normal or the radial component, must be perpendicular to this absolute acceleration. Not perpendicular, but it has to be of the same direction sense as that of our link. Since A here is our center of rotation, that is why our ABA normal is moving towards A. If B is the center of rotation, then ABA normal will move towards B. So again, you draw the value that we got earlier ago, the value of the relative acceleration of B with respect to A normal on the head of the absolute velocity of absolute acceleration of A. Yan, in the same direction going to A, parallel to the link that we have. That is the normal component. And then for our tangential component, we also learned that the tangential component of the acceleration is just perpendicular to the link. That is why, and that is connected to the head. We connect it to the head of the normal component of the acceleration, as you can see here. But we do not have the value yet of this tangential component of the relative acceleration of B with respect to A. All we know is that it is perpendicular to the link AB. So as you can see here, we have normal component parallel, and then we have tangential component that is perpendicular. So again, we draw the normal component from the head of the absolute acceleration of A, and then connect the tangential component to the head of the normal. And since we know from the given that our B is moving towards the direction sense of M, so all we have to do is just to draw a line that is parallel to that direction from the pole Q. So in this way, we were able to solve for the absolute acceleration of point B. That is how you solve the absolute acceleration of point B. So you can connect that you can get the value of the tangential component of the relative acceleration of B with respect to A. As you can see here, it is consistent with our equation that it is consistent to our equation that our absolute acceleration of B is the sum of the vector components absolute acceleration of A plus the absolute acceleration of B with respect to A relative to A normal plus the absolute acceleration of B with the relative acceleration of B with respect to A tangential. So that is why we have this value here. All you have to do is just to measure this one in your paper and then convert it to the actual size using acceleration scale. So that is how you draw the acceleration polygon. This now refers to our acceleration polygon. So as you can see, there are some differences in drawing the acceleration polygon as that of the velocity polygon. So this time, it does not necessarily have to be, the length here does not have to be entirely perpendicular to the actual drawing. Our final answer would be, so our absolute acceleration of point B is measuring QB in our acceleration polygon. You measure this length and then multiply it with our acceleration scale. And then for our angular acceleration of AB, so this is the angular acceleration of this floating link, that is equals to this formula that we also have a while ago. So that the relative velocity of B with respect to A tangential divided by AB.